we have our next speaker is Professor Sungyon Lee. She is an associate professor at the Department of Mechanical Engineering at the University of Minnesota. She works on a wide range of problems, including drops and bubbles, particle-laden flows, viscous fingering. So again, we can see an animation of a viscous fingering phenomena, I guess, with particles loaded there. So I guess this is what we'll be hearing, and the stage is all yours.
All right, thank you very much. Let's see, I just want to make sure. So everybody can hear me?
Yes, yes.
Okay, great. Yeah, thank you so much for having me. It's such an honor to be included in this symposium, and happy birthday to Professor Bala. I don't think we've ever met, but I've went back and read a lot of your papers, and it's really an honor to be included in your celebration. So today, hopefully I can bring something a little bit different to the table, because the types of problems that I tend to work on happens to be very slow and viscous. So it's probably in a slightly different regime from a lot of the speakers that are presented here. Regardless, I do work a lot in multiphase flows, as you can see in the problems that are represented in this one snapshot. Another thing I want to say is that in our group, we like to actually take complicated phenomena and reduce them down to a simple tractable problems by combining both simple tabletop experiments and simple mathematical models. So the word simplicity is the word I use a lot, and that's really, hopefully you'll be able to see in my short presentation today. Out of very different problems that we work on in the group, I will today focus on one in particular that involves particle-laden flows and instabilities that you see in this particular flow phenomena. So for the last few years, we've been sort of chasing this question that I highlighted here. We're kind of interested in understanding situations in which the presence of suspended particles in the liquid phase can dramatically modify the dynamics of fluid-fluid interface. So in my PhD, I studied the interfacial dynamics a lot. During my postdoc with Andrea Bertozzi, I worked on particle-laden flows. So in some ways, I wanted to bring those two areas together in my faculty career. So just to demonstrate that, I'll start with a very, very simple flow. So here we have two parallel plates. So Healy-Shot cell with two glass plates that are parallel and closely spaced. And we drill a hole on the bottom plate, and we can basically inject oil phase through the hole. So we can you can see the oil displacing air and flowing out radially. And as you might expect, this is a very simple experiment, and we don't expect anything to happen, and thankfully nothing does, as we understand that the invasion of more viscous fluid into less viscous fluid, in this case air, is supposed to be stable. So with this as our very simple reference experiment, what we wanted to do next is actually to see if we were to repeat this experiment, but instead of just pure oil, if we injected particle and oil mixture, we wanted to see whether something different might happen. Here, the particles are not very special. The oil is silicon oil. The particles are these plastic particles that are quite large. So these are about 300 microns. So definitely non-colloidal particles. And when we repeat the experiments as we've done before, we do indeed see something very different. We see the formation of these regular particle clusters and very prominent interfacial deformations. So this is what we've been calling particle-induced viscous fingering, and this is something we've been studying for a while in our group the last few years. But I need to highlight that this was first discovered by Tang and colleagues in their very insightful paper back in 2000. So today I want to first explain the physical mechanism behind this particle-induced viscous fingering. And if there's any time left, discuss a new model that we've developed describing one of the features leading up to the fingering, not maybe the fingering itself. And of course, as we understand that this phenomena, whatever the mechanism is due to the presence of particles, it should be no surprise that as we increase the particle concentration going from right to left, the more pronounced and these fingering phenomena become. All right. So first, I want to explain the mechanism. If nothing else, this is one thing I want to be able to do in today's talk. So let's just imagine the flow from the side view. And for now, let's even forget about the fluid-fluid interface, forget about the particles. We all know that in flow between parallel plates, we're going to have this nice parabolic flow profile. If we happen to have non-colloidal particles present in the system, what we can expect is that these particles will preferentially migrate and collect near the center line where the shear is minimum. So this is called shear-induced migration, the term that was first coined by Layton and Akrivos back in 1980s. So once we actually understand that this phenomenon happens, then it's not so difficult to reason out that the average particle velocity across the cross-section, let's call it VRP, must be ever so slightly greater than the average mixture velocity. And that's of course because there are more particles near the center where the flow is maximum. And now if we bring back the fluid-fluid interface that's supposed to be moving with a mixture velocity, then we would actually expect these particles to eventually catch up to the interface and actually accumulate there. So this is a very simple hypothesis that we can actually test in the lab. So we tried this experiment where we injected oil ahead of the suspension, and you can see that eventually, or rather quickly, the particles do catch up to the moving interface. And if we wait long enough, there will be a very clear accumulation. So in our current system, what we can expect for sure is the accumulation of particles on the interface. And of course, this is also something we can measure in the lab as well by taking a typical experiment, top-down experiment like this, and by just converting the light intensity information and relating back to the depth average particle concentration phi bar using the Beer-Lambert law, we can plot the particle concentration over the radial distance that clearly shows accumulation or rise in particle concentration in R. And it also interestingly comes back down, but hopefully we'll have a time to talk about that feature as well. So accumulation happens, we understand why, and we can also measure it quantitatively based on our experimental images. But once we establish this, the question is, how do we just understand the occurrence of fingering? Well, we said early on that the invasion of more viscous fluid into less viscous fluid is stable. So if we just think in terms of suspension invading air, you would expect this system to be stable. However, inside the suspension, now we've created a condition for viscous fingering, as we have less viscous or less concentrated suspension invading more viscous or more concentrated suspension inside the suspension, right? So this is exactly the condition for viscous fingering, which has been studied for many, many decades, starting with Saffman-Taylor, and it's actually being investigated even actively now, whether it's between two immiscible fluids or miscible fluids. So in our scenario, the fingering is happening within the miscible fluids, since it is happening within the suspension. So just to summarize, so the mechanism is quite straightforward. We first have particle accumulation on the interface due to the effect of shear-induced migration, which leads to this condition, destabilizing condition within the suspension. So we have the occurrence of miscible fingering, followed by the interfacial deformations. And today, for the rest of the time, actually, I want to spend just more time talking about particle accumulation and the model interesting feature that we found within the accumulation itself. So as I discussed earlier, we can even go ahead and measure the particle concentration over the distance, and we understand the physical mechanism. There are basically two basic features we need, right? We need shear-induced migration of particles across the streamlines, so in the Z direction, which allows the particles to assume a slightly faster speed than the background speed, and the presence of the advancing interface that's basically there to catch the particles that leads to accumulation. So the mechanism is very simple. However, something that we didn't understand and that we saw actually very early on in our experiment is that when we go ahead and take our particle data and normalize it by the position of the interface, capital R, the particle concentration data seems to collapse in a very, very nice way. And of course, if you go ahead and kind of zoom in near where the accumulation happens, this is not an exact collapse. As you can see, there are more and more particles accumulating on the interface over time. However, the overall length scale of the particle accumulation and even the feature of the particle concentration decreasing near the interface is very well, they very well collapse into a single curve. So the question we've been actually chasing for the last few years is, why do particles accumulate in this very peculiar and clearly self-similar manner? And we wanted to see whether this would come out naturally from a simple mathematical model. So that's what we'll be talking about for the rest of the time. So we decided to use suspension balance model. So this is a very well-established continuum approach, first introduced by Knott and Brady back in 1994. So just to summarize it really quickly and crudely, this basically takes mass and momentum conservation of the mixture phase, so both particles and liquid, as well as that of the particulate phase. And we can basically combine them two by looking at the various constitutive relationship, which I've written out here, but I'm not going to the detail. But maybe one interesting feature I want to point out is that this particular constitutive relationship captures the buildup in a normal stress in the particulate phase, which is proportional to the shear rate gamma. So the effect of shear-induced migration that I've been talking about from the very beginning of the talk will be captured through this constitutive relationship. So what we wanted to do is start out with these very general governing equations. Oh, by the way, the Reynolds number is really low, so we don't have any inertia in these particular governing equations. So we wanted to take these very general governing equations, but find a way to simplify them by kind of looking for the separation of the occurrence of natural separation of length scales in the problem. So first we have H over R being very, very small. We call this epsilon, small parameter epsilon. So R naught is the characteristic radial distance that's about 10 centimeters in our experiment, while H is the gap thickness H, which is pretty much millimetric. So this is confidently a very small parameter. But another small parameter we need, and which is actually implicitly assumed in the problem, is that the particle size D must be much, much smaller than the gap thickness H, right? So that justifies using the continuum approach. So we introduce another small, in this case, a large parameter chi, which is a ratio between H over D times squared. But another interesting separation that we wanted to take advantage is a separation of time scale. So here I have tau z much, much less than tau r. So let me just explain that very quickly. So tau z refers to the characteristic timescales of particles migrating across the streamlines due to shear-induced migration. And we assume that to be much, much smaller than the characteristic timescale of particles just following the radial flow, tau r. And we can justify this separation by noticing that in all our experiments, the transient regime that happens as the particles first enter the channel and undergo shear-induced migration is always consistently smaller than the overall, the fully developed regime followed by the accumulation. So based on these observations, we're going to make these claims of separation of timescales. Combining it all together, what we're going to utilize is to simplify our equations based on lubrication approximation. So epsilon is very small, but as well as taking advantage of these small time scales, we're going to expand our dimensionless variables in the order of epsilon chi. So what is going to follow is pages and pages of math, which I'm not going to show you, but I really have to give credit to Balachandar's paper in JFM because we're basically following the theoretical framework that he first introduced in his paper. So just trying to skip to the key part here. So go to our governing equations, get the solution order by order. And what we ultimately want is the depth average particle transport equation to solve for phi bar. So the depth average particle concentration. So here I believe I only have 1 minute left, so I'll really try to sum up. But this basically has two features. One is the advection term that comes from the leading order particle flux solutions. And I'll just highlight the fact that here, if you just look at our leading order solutions and plot the particle concentration over Z, I hope you can see that you can see the features of shear-induced migration as there are more particles near Z is equal to 0, which is the center line, compared to Z is equal to 0.5, which is the walls. So putting it all together, we can find particle flux at the leading order. The next term here is what we call Taylor dispersion term, because it has a second derivative in phi bar. And this term comes directly from the particle flux at the next order, epsilon chi. And to understand the physical feature meaning of this particular term, we have to go ahead and plot this dimensionless numerical function S, because there's no analytical solution for this. It just took a lot of numerical integrations that I'm not showing you here. But just to highlight that this particular function is actually negative. And that basically means that when partial phi bar partial r is positive, or when the particles accumulation is happening, this term acts to reduce the total particle flux, which means that it actually allows the particles to accumulate gradually. So this particular term is very important for the gradual accumulation of particles. And next, of course, I need to show you why this is self-similar, but I'm not actually, I'll just skip to the very solution because I understand I'm running out of time. So here, so if we actually go back and solve this equation PDE numerically, and we only have one empirical parameter here, epsilon chi, we can actually capture the self-similar accumulation of particles that we observed from the experiment quite effectively. And the model was very simple because we didn't account for the secondary flow near the interface. We didn't actually account for, the shape of the meniscus. Despite all that, just using this very simple continuum model, we're able to capture this self-similar behavior. So I'll just end my talk here. Just to summarize, so we introduced particle-induced viscous fingering, which comes from particle accumulation on the interface, which creates this condition for viscous fingering within the suspension. But we spent most of time talking about why the particle accumulation happens to be self-similar. So there are basically three basic features here I wanted to emphasize. The key here is the shear-induced migration of particles across a streamline, the presence of impenetrable interface that catches the particles, and the physical effect of Taylor dispersion to smooth out the accumulation. Those three ingredients were sufficient to actually create this condition for self-similar accumulation. And there's a lot more work we're doing in this area, but in the interest of time, I'll just end right here and I'll be happy to take your questions.
Sungyon.
Thanks a lot for the talk. Yeah.
Oh,
Professor
thank
Bala,
you.
please go ahead.
It was a great talk. I have one simple question. Here in the, when you look from the top view, you have a point source and you have a cylindrical front moving out.
Yes.
Instead of that, if you had a line source, for example, and a planar front moving, would you see these instabilities? That was my question.
Yes, actually, we do see this instability in the rectangular channel as well. Actually, we just completed a set of experiments in the rectangular channel. So in this particular experiment, you will not see any instability because the concentration is quite low. But yeah, if we increase the particle concentration in the rectangular channel, you will still see particle accumulation and very clear occurrence of particle viscous fingering. Actually, let me try to see, because the experiments are very dramatic. Oh, I think I put that out there. But I guess, yeah, this is actually an experiment in a rectangular channel. Yeah, you can clearly see it. But actually, we don't expect this accumulation to be self-similar anymore. I think that just came naturally out of the cylindrical geometry. So we actually expect that when we process this data and actually try to calculate the particle concentration over the distance, I expect it will lose the self-similarity, but we actually haven't gotten to the processing yet.
Yeah, the reason I asked this is in high-speed flows, particle-laden gas flows, and so on. These fronts also become fingering instabilities.
Oh,
Happen.
okay, that's interesting.
That is due to Rayleigh-Taylor instability, and it doesn't happen so much in the planar, and happens only in the expanding cases of cylindrical and spherical geometry. But clearly this is a viscous fingering effect, very different, but fascinating.
Right,
Thank you.
right. Yeah.
I guess a Rayleigh-Taylor is probably possible if she rotates the setup.
Yeah.
I guess so. Yeah.
So I had a couple of questions. So like, there are two time scales in the problem that you're talking about, an advection time scale and the shear induced migration time scale.
Yes.
Now, those time scales, I mean, but there is also concentration, which doesn't seem to depend on the time scale, if I understand correctly, or does it depend on the, so concentration is another parameter, and you found that below a certain concentration, you don't get this instability. Is there a dramatic change in the behavior with concentration, or is it like a subtle continuous increase? And
so yeah, go ahead. Yeah.
And the follow-up one part of that was, the second part of the question was, if the concentration is low, do you have to wait longer to see the instability? I mean, that may lead to limitations in your experiment of how far can you go, but particles may eventually catch up.
Yeah, I mean, I love your questions because they're very insightful. So maybe I need to say that when we say there's fingering or no fingering, we are basically saying within our experimental setup. So that's like a little disclaimer. So yes, so within this, whatever the Helicia cell size is, I think, yeah, maybe 25 centimeters across, we are saying, okay, there's fingering or no fingering. So yeah, so the length, there is a limit to the total length scale. And I think another thing we have to watch out for when we say, then imagine an infinitely large Helicia cell and ask the question, will there be fingering or no fingering? These particles that we're working with are quasi-neutrally, neutrally buoyant, meaning their density is slightly greater than the suspending liquid. So there is a chance that if we make the Helicia cell infinitely large, maybe over time they'll eventually accumulate to the interface, but at the same time, they'll eventually settle to the bottom of the plate as well, which would actually eliminate their accumulation. So they're sort of, if we make the cell larger, then I think there's an extra effect of particles, the Stokes sinking that we have to settling, which we have to account for. So which we're not doing right now. But going back to your earlier question about the effect of particle concentration. So actually, although in the current, when we frame the time scale for shear induced migration, I didn't include particle concentration. But what's well known in the literature is that shear induced migration is only observed for concentration maybe above 15 or 20%. I don't know exactly the number, but so in reality, the concentration does matter. And if you have a concentration that's below, for sure below 10% in our experiments, we actually do not observe accumulation even within our setup, because I think that eliminates this occurrence of shear induced migration. And without it, we don't see any interesting. So shear induced migration is really the key. And that itself seems to be particle concentration dependent.
Okay.
Yeah.
I have one more question on the asymptotics, but we have a question in the Q&A here. We'll take that question perhaps first. So Nadeem,
I have a question. Did I end my talk too early, or did
No, perfect.
Okay,
timing.
so I did be 15 minutes, right? Because
Yeah,
I
so
rushed
actually,
through. I thought I was running out of time.
So we're taking advantage of the 10-minute break that we have.
Oh, great. Okay.
Okay. So Nadeem is asking this question: would you see this instability if the flow were to be driven by the particles, such as in gravity currents, or more appropriately, particle-laden buoyancy-driven flows?
So maybe I could you repeat the first part of the talk?
You could maybe
Okay.
it'll be easier if you could just take a look at the Q&A. Do you see the
Yeah,
questions?
okay, I'll do that. Okay.
Do you see the question?
Yes, yes. Yeah, I mean, I think so. We just have to, I guess I need to answer this question carefully. I don't see why it wouldn't, but then now I also have to think about the density difference as well. Because depending on the orientation of the flow, the particle accumulation, let's see, how do I say this right? I'm just trying to relate it back to the original Safman-Taylor work, because when they do their viscous fingering experiments in a vertical setup, depending the orientation and the density of the invading and defending fluid, they can either eliminate viscous fingering or even accelerate the viscous fingering. So I think the answer to this question is, in general, yes, we can find the right configuration where we will indeed see particle-induced viscous fingering even with effective gravity, but I think we just have to play around with the right configuration. And yeah, because that goes back to Safman-Taylor's original experiments. Yes. Yeah.
So he says, I've seen similar instability in particle-laden flows.
Yeah. So actually that's the work that I also worked on with Andrea Bertozzi at UCLA, just the free surface flows going down an incline. I think the mechanism is different because in that case, we have a free surface on top. So it's not quite the same viscous fingering that we observe here, where we have a confined channel. So everything is driven by the pressure gradient. Whereas on the free surface flows, you have atmospheric pressure on top so in that, I guess they call it capillary ridge instability. And that mechanism of fingering is, I think, not exactly the same as this viscous fingering. But yes, I know that work very well as well. Yeah. Oh, and your own work. Okay, cool. Yeah.
So I had one question on the asymptotics that you've set up. So you have this parameter epsilon chi has to be less than 1. But your chi actually has a particle diameter in the denominator.
Yes.
So if you were to keep reducing the particle size, your particle size, if I remember, were about 330 microns. So if you keep
so for the demonstrative experiments, I showed you with 300 microns, but for the continuum modeling experiments, they're about 100. Yeah, so they're maybe 10 times smaller than the
so if you keep reducing the particle size, then chi keeps becoming larger.
Yeah.
And so does the asymptotics break down?
Yes, I would expect the asymptotics to break down. So it's like the ratio of particle size to the gap has to hit a sweet spot, because if the particles are too big, you should definitely question why we're using continuum model. But if the particles become too small, especially when they start reaching the colloidal limit, we actually don't expect any of this interesting phenomena such as shear-induced migration across the streamlines to actually happen, in which case it would also eliminate everything that we observe. So that's why this, chi is an important parameter, so it cannot be too big or too small. Yeah.
Okay. Yeah. Okay. So if there are no more questions, I think we'll thank all the 3 speakers. Thanks to Sungyon Lee for this talk, wonderful talk, and thanks to the other speakers. And then I can see a virtual clap from Professor Bala. And so we'll have the next session in about a minute, actually. So
okay, all right.
Yeah,
it's really great to meet you, Professor Bala. Happy birthday. And thanks for the invitation again. Bye.
Thank you.